November 9th, 1967. 7 a.m., Kennedy Space Center, Florida. A crowd of 3,000 engineers stands behind reinforced blast shields 3 miles from the launch pad. Most of them have not slept in 36 hours. Some have not slept properly in 3 years. What they are about to witness has never happened before in human history. On pad 39A, a machine stands 363 feet tall. That is taller than the Statue of Liberty plus its base, plus another 12 stories on top. It weighs 6.2 million pounds fully loaded. It contains 3 million individual parts, assembled by over 400,000 workers across 20,000 companies spread across the entire United States. In 40 seconds, this machine will attempt to produce 7.6 million pounds of thrust simultaneously. To understand how impossible that number is, the most powerful aircraft engine ever built produces roughly 115,000 pounds of thrust. The Saturn V first stage produces 66 times that amount, not from one engine, from 5 engines burning simultaneously. But here is the secret that every history book leaves out. Every single calculation required to design, test, and launch this machine was done without a single supercomputer. The most powerful computer available to NASA engineers in 1961 had less processing power than the calculator app on your phone today. The guidance computer that would eventually steer this rocket to the moon had 4 kilobytes of memory. Your email app uses more memory than that just to open. NASA built the most complex machine in human history using slide rules, paper notebooks, and physical testing. And in the process, they solved 3 engineering problems that the entire scientific community said were mathematically impossible to solve. This is the story of how they did it. But what nobody knew on that November morning was that just 18 months earlier, this program had been on the edge of complete cancellation. An engine had exploded during testing so violently that it destroyed an entire test stand, and the man responsible for fixing it had just proposed a solution so bizarre, so counterintuitive, that his own engineers thought he had lost his mind.
To understand why the Saturn V was necessary, you need to understand what America was facing in 1961. On April 12th of that year, Soviet cosmonaut Yuri Gagarin became the first human being in space. The entire world watched. The message was unmistakable. The Soviet Union, a nation that had been devastated by World War II just 16 years earlier, had beaten the most technologically advanced nation on Earth into space. 3 weeks later, President Kennedy stood before Congress. His words were direct. "I believe that this nation should commit itself to achieving the goal, before this decade is out, of landing a man on the moon and returning him safely to Earth." The engineers in the room understood exactly what he was asking. The most powerful American rocket at that moment could lift approximately 40,000 pounds into low Earth orbit. Getting a crew to the moon and back required lifting at least 310,000 pounds. That gap was not an engineering challenge, it was an engineering impossibility by every existing standard. The moon is 239,000 miles away. It has no atmosphere to slow an approaching spacecraft. It has no landing strip. It has no fuel for the return journey. A crew would need to carry everything. Every kilogram of fuel for the lunar landing required more fuel to lift it from Earth, which required more fuel to lift that fuel, which required more fuel still. The mathematics created what engineers call a tyranny of the rocket equation. To send humans to the moon and bring them back, NASA needed a rocket roughly 10 times more powerful than anything ever built, and they needed it within 8 years. Werner von Braun, the German-born rocket engineer who had led the V-2 program during World War II and was now directing NASA's Marshall Space Flight Center in Huntsville, Alabama, proposed the solution: a three-stage rocket using clustered engines of unprecedented power. He called it the Saturn V. But the moment his engineering teams began designing the first-stage engine, they discovered a problem that would consume 5 years, destroy dozens of test engines, and nearly end the Apollo program entirely before it began. The problem had a technical name: combustion instability. But the engineers working on it had a simpler name. They called it the monster.
Think of a car engine. Fuel and air mix inside a cylinder. A spark ignites the mixture. The explosion pushes a piston down. It is controlled, predictable, rhythmic. Now imagine scaling that process to produce 1.5 million pounds of thrust from a single engine. Every second, the F1 engine burns 3 tons of fuel. Liquid oxygen and a refined kerosene called RP1 are pumped into a combustion chamber at pressures exceeding 1,000 pounds per square inch. The resulting combustion produces temperatures of approximately 5,600 degrees Fahrenheit. That is hotter than the surface of the sun. At that scale, combustion does not behave like a car engine. It behaves like a living thing. The problem the Rocketdyne engineers discovered in 1959 was this. Inside the F1 combustion chamber, the burning propellants created pressure waves. These waves bounced back and forth across the chamber at frequencies between 200 and 600 times per second. Under certain conditions, those pressure waves synchronized. When they synchronized, they amplified each other. The pressure spike became catastrophic. Engines exploded, not gently, violently. During testing at Edwards Air Force Base in California, engineers watched F1 engines destroy themselves without warning. A test would begin normally, thrust would build as expected. Then, without any detectable change in operating conditions, the engine would detonate. The entire thrust chamber, made of steel thick enough to stop rifle bullets, would tear apart in milliseconds.
But here is the engineering challenge nobody had solved before. The explosions were not consistent. An engine configuration that failed catastrophically on Tuesday might run perfectly on Wednesday with no changes made, then fail again on Thursday. The engineers could not find a pattern. They could not build a mathematical model, because in 1961 there was no computer powerful enough to simulate combustion behavior at this scale. The engineers were flying blind, completely. Here is why this problem was so difficult to solve without modern computing. Today, engineers simulate combustion using computational fluid dynamics software. They can model exactly how fuel and oxidizer mix, how pressure waves form, and how those waves interact, all on a computer screen before a single test is run. Problematic designs are identified and fixed in software. Only validated designs get built and tested. In 1961, none of that existed. Every theory had to be tested physically. Every physical test could destroy a $1 million engine. And after the test, engineers had to analyze high-speed camera footage, pressure sensor recordings, and physical debris to understand what had happened. Then they had to hypothesize a fix, build a new engine component, and test again. Between 1959 and 1964, Rocketdyne engineers ran over 2,000 separate combustion instability tests. They tried injector redesigns. They tried chamber geometry changes. They tried different fuel ratios. They tried different pressure levels. The monster kept winning. By 1962, NASA program managers were having private conversations about whether the F1 engine could ever be made stable. Some began exploring alternative approaches, using smaller, clustered engines instead of the giant F1s. But von Braun rejected this.
Clustering smaller engines multiplied complexity. More engines meant more potential failure points. More failure points meant lower reliability. On a crewed mission to the moon, lower reliability was not acceptable. The F-1 had to work, and it had to be stable. The real breakthrough came not from a mathematical solution, not from a computer model, but from an idea so unconventional that every experienced rocket engineer in the room initially laughed when they heard it. The proposal was this: if we cannot predict when the engine will become unstable, we need to deliberately trigger instability on command and then observe exactly what happens.
The engineer who proposed this approach was Paul Castenholz, a combustion specialist at Rocketdyne. His reasoning was direct. The problem was that engineers could not study instability because they could not control when it happened. Test after test, the engine either ran perfectly or destroyed itself randomly. There was no way to observe the instability developing. There was no way to see what conditions caused it. There was no way to test whether a proposed fix actually worked, because the engine might run perfectly for 10 minutes and then become unstable at minute 11. Castenholz proposed a solution that required extraordinary courage to approve. Put a small explosive charge inside the running engine. Not to destroy it, not as an accident, deliberately, on purpose. The charge was a small package of black powder wrapped in a Teflon coating. Teflon is heat-resistant. It allowed the charge to survive in the combustion environment long enough to be triggered at a specific chosen moment. When engineers fired the charge, it created a precisely controlled pressure pulse inside the running combustion chamber. This triggered instability intentionally, on command, at a moment when engineers were ready to observe and record everything. The technique had a name: the bomb test. Here is how a typical bomb test proceeded at the Rocketdyne test facility in 1963. 6 a.m. The team arrives. 12 engineers gather around a single F-1 engine mounted on a test stand built specifically to survive engine explosions. The stand is constructed of reinforced steel and designed to contain a complete engine detonation. Even so, engineers operate from a concrete blockhouse 500 feet away. 7:30 a.m. The bomb package is installed. A Teflon-coated black powder charge, approximately the size of a large coin, is mounted at a precisely calculated position on the injector face. The charge has an electrical trigger connected to the control blockhouse by a wire that runs outside the engine. A technician checks the electrical connection 3 times. 8:15 a.m. Engine start. Liquid oxygen and RP1 begin flowing into the combustion chamber. Turbopumps spin up. The engine builds to full thrust. The sound at 500 feet is physically painful even through ear protection. 8:17 a.m. At exactly 2 minutes of stable operation, the lead engineer gives the signal. The electrical trigger fires. The small bomb detonates inside the running engine. What happens next determines everything. If the pressure spike from the bomb dissipates within 400 milliseconds and the engine returns to stable operation, the injector design passes. It can recover from intentional disturbance. If the pressure spike grows, amplifies, and the engine begins destroying itself, the design fails. Engineers cut fuel flow and the engine shuts down. Sometimes the shutdown comes fast enough, sometimes it does not. 8:17 a.m. and 0.4 seconds. Engineers watch the pressure gauges. They are measuring oscillation frequency and amplitude in real time. With the previous injector design, the pressure spike grew catastrophically. The engine had to be destroyed. With the new baffled injector design, the readings are different. The spike appears sharp and clear on the instruments, then it flattens. The oscillations decay. Within 350 milliseconds, the chamber pressure returns to normal. The engine continues running, stably. For the first time in 4 years of testing, an F1 engine has survived deliberate destabilization. But the bomb test had only solved half the problem. The baffles on the injector face prevented destructive resonance from amplifying, but they created a new problem. And this new problem threatened not the first stage, but the second. Something was shaking the entire rocket violently enough to injure astronauts and potentially tear the vehicle apart during flight. The Pogo problem. The second major engineering crisis had a name borrowed from a child's toy: Pogo oscillation, named because the rocket behaved like a pogo stick, bouncing up and down rhythmically during flight.
Here is what caused it. The 5 J2 engines of the Saturn V second stage burned liquid oxygen and liquid hydrogen. As propellant drained from the tanks, the tank walls flexed slightly. This flexing changed the pressure in the feed lines. The pressure change affected engine thrust. The thrust change accelerated the rocket differently. The acceleration change affected how propellant sloshed in the tanks. The sloshing changed tank pressure, which changed feed line pressure, which changed thrust, which changed acceleration. A feedback loop, self-reinforcing, growing with each cycle. During the second unmanned Saturn V test flight in April 1968, the Pogo effect became violent enough to trigger automatic engine shutdown on 2 of the 5 second stage engines. Had this occurred on a crewed mission, the astronauts would have experienced oscillations severe enough to blur their vision and prevent them from reading instruments. The engineering team, led by Marshall Space Flight Center specialists, identified the root cause within 6 weeks. The solution required modifying the center engine of the second stage. Engineers installed a helium gas accumulator in the liquid oxygen feed line. Think of this as a shock absorber for the fuel line. When pressure fluctuations tried to create a feedback cycle, the helium accumulator absorbed the pressure pulse before it could amplify into the engine. The modification was tested on the next flight, Apollo 8, December 1968. The Pogo effect was gone completely. The computer that wasn't there. But both of these solutions, the baffled injector and the helium accumulator, were developed using a method that modern engineers find almost impossible to believe. There were no simulation tools, no computational models, no finite element analysis.
Every test was physical. Every measurement was analog. Every calculation was done by hand, using slide rules and paper. The guidance computer that eventually steered the Saturn V to the moon had 4 kilobytes of RAM and ran at 2 megahertz. To compare, the cheapest smartphone sold today has approximately 4 gigabytes of RAM. That is 1 million times more memory. The Saturn V guidance computer had less processing power than the microcontroller inside a modern digital thermostat. So how did 400,000 engineers design a 3 million part machine without computers? They divided the problem. Each engineering team owned one system, not the rocket, one specific system. One team owned the F1 injector geometry. Another team owned the turbopump bearings. Another owned the guidance electronics. Another owned the stage separation explosive bolts. Each team became the world's absolute authority on their specific component. They tested obsessively. They documented everything. They communicated with adjacent teams through formal interface specifications that defined exactly what each system would deliver and exactly what it expected to receive. The entire Saturn V was a 3 million part system managed through disciplined human specialization rather than computational modeling. Von Braun himself reviewed test data personally every single week. Not reports, raw data.
He attended every significant test firing. He read every failure analysis. He understood every major system well enough to ask the specific technical question that revealed the real problem beneath the reported problem. This was engineering management as a substitute for computational power. And it worked.
November 9th, 1967. Back on pad 39A. At 7:01 a.m. Eastern Time, the 5 F1 engines of the Saturn V first stage ignite in sequence. The ignition sequence takes 8.9 seconds. This is not accidental. The staggered ignition prevents the simultaneous pressure surge from all 5 engines from structurally overloading the vehicle. At 7:01 a.m., engine 5 ignites. At 7:02 a.m., engines 1 and 3. At 7:03 a.m., engines 2 and 4. By 7:10 a.m., all 5 engines are at full thrust. The sound reaches the engineers behind blast shields 3 miles away 2 seconds later. Several of them later describe it not as sound, but as physical pressure. The ground shakes, instruments rattle, coffee cups fall from consoles. The Saturn V clears the tower at 7:18 a.m. It has been on the ground for the last time. The vehicle climbs through 50,000 feet in 68 seconds. The 5 F1 engines burn for exactly 159 seconds, consuming 4.4 million pounds of propellant. The first stage separates cleanly at an altitude of 38 miles. The 5 J2 engines of the second stage ignite. The third stage ignites. The spacecraft reaches orbit. Every single engineering solution works exactly as designed. Every baffle performs. Every helium accumulator performs. Every guidance calculation performs. At Mission Control in Houston, the flight director picks up his microphone. We have confirmed orbital insertion. The Saturn V has performed nominally. In blockhouses and control rooms and engineering offices across 20 states, 400,000 people who had spent years solving impossible problems with slide rules and physical tests understand what that word means. Nominally. As designed, as calculated, as predicted, without a supercomputer, without simulation software, without computational fluid dynamics. But here is what makes this achievement even more remarkable. The Soviet Union, racing to beat America to the moon, had their own super heavy rocket under development, the N-1. It had 30 engines on its first stage compared to America's 5. And it had something the Saturn V did not. It had failed 4 times. Each failure was catastrophic. The third failure, on June 27, 1971, created the largest non-nuclear explosion in human history. The Saturn V never failed, not once. In 13 launches, it never lost a single payload. The Saturn V flew 13 times between 1967 and 1973. It carried 12 men to the surface of the moon. It carried the Skylab space station into orbit. It never failed a mission. The engineering solutions developed for the Saturn V influenced every large rocket program that followed. The bomb test methodology developed by Paul Kastenholz became standard practice for high-thrust engine development. When Rocketdyne developed the Space Shuttle main engine in the 1970s, combustion stability testing used the same basic approach. When SpaceX developed the Merlin engine for the Falcon 9 rocket, they referenced combustion stability testing protocols that traced directly back to the F1 program. The Pogo suppression system developed for the Saturn V's second stage became fundamental to liquid-fueled rocket design. Every major rocket flying today incorporates some form of propellant feed line dampening to prevent oscillation feedback loops.
The engineering principles are the same ones worked out by Marshall Space Flight Center engineers in 1967 and 1968. The management methodology, using strict human specialization as a substitute for computational power, gave birth to what is now called systems engineering. The formal interface specification approach, where each component team defines exactly what their system delivers and expects, is today the foundation of every complex engineering project on Earth. From commercial aircraft to nuclear power plants to semiconductor fabrication to the phone in your hand. The Saturn V engineers invented modern systems engineering methodology, not because it was theoretically ideal, but because without computers, it was the only approach that could work. Consider what would have happened if Paul Castenholz had not proposed the bomb test. Without a method to deliberately trigger and study combustion instability, the F-1 engineers might never have developed the baffled injector design. Without a stable F-1 engine, there was no Saturn V first stage. Without a Saturn V, there was no Apollo 11. On July 20, 1969, Neil Armstrong would not have stepped onto the lunar surface. The Cold War space race would have continued with an uncertain outcome. The satellite communications networks, GPS navigation, and weather prediction systems that depend on the launch technology descended from Saturn V, none of those would exist in their current form. One engineer's counterintuitive idea, deliberately exploding a running rocket engine, changed the trajectory of human civilization.
Today, Saturn V remains the only rocket in human history capable of sending humans beyond low Earth orbit and returning them safely. The record it set in 1969, lifting 310,000 pounds to the moon, has never been matched. The SLS rocket being developed by NASA today is specifically designed to reclaim this capability. Its first stage engines are direct descendants of the Space Shuttle main engine, which was a direct descendant of the F-1. The rocket you will watch carry astronauts to the moon in the coming years carries DNA from that 1967 test stand at Edwards Air Force Base. From the moment Paul Castenholz put a small black powder bomb inside a running engine and watched what happened. Here is the philosophical truth that the Saturn V engineers demonstrated. Computational power does not solve engineering problems. Human understanding does. The computer is a tool for implementing solutions that human minds have already conceived. The Saturn V engineers had less computing power than a pocket calculator, but they had something no computer has ever possessed: the ability to ask the right question when everyone else was asking the wrong one. The right question was not, how do we prevent combustion instability? The right question was, how do we study combustion instability when it is unpredictable? The answer changed everything. This channel exists to uncover the engineering secrets that mainstream history ignores. Not who won the battles, not which nation launched first, but how the specific technical problems were identified and solved by specific engineers whose names most people have never heard. If you found this story remarkable, subscribe and turn on notifications. Leave a comment with one question. What is the most surprising detail you learned today? Thank you for watching. Stay curious.